Welcome to the UGC lecture series. This is the EPG Pathshala lecture series on computer science, and we are talking about the paper data structures. In this particular module, we will be talking about another very interesting graph algorithm called the shortest path algorithm. As in many graph algorithms, we have more than one algorithm to solve the same problem, the shortest path algorithm, shortest path. So, let us look at the shortest path algorithm in this module. The first algorithm we will be looking in detail. Before that, we will be discussing the contents of the concept of shortest path. So, these are the people responsible for creating this module, and the learning objectives of this module are to understand the shortest problem and its variants. That is, there are many variants to the shortest path, will be a problem. So, we will be discussing that. Then we are going to look at some important properties of shortest path. Then we are going to explain the Dijkstra's algorithm, which is a very popular algorithm for shortest path, and we are going to illustrate the Dijkstra's algorithm with an example. So, the terms associated with this are shortest path, greedy algorithm and relaxation. We will talk about what is a relaxation as we go along. So, let us first define in layman's terms the meaning of shortest path algorithm. So, given a weighted graph and two vertices u and v, we want to find a path of minimum total weight between u and v. This is the simplest definition of a shortest path problem. So, you are given a weighted graph and you have two vertices u and v. You want to find a path. There are many paths that can take you from u to v. You want to find the path with the minimum total weight. Sometimes it is called as total weight, sometimes it is called as length, sometimes it is called as distance, it does not matter. So, the length of the path, that path, find a path with total weight is the sum of the weights of its edges. So, that is how we are defining the minimum. So, why we are saying distance, because we are talking about shortest. So, for example, you want to find the shortest path between Bangalore and Madurai. So, that is an example. Now, this type of connecting cities is a typical example of shortest path. You can look at similar applications as internet packet routing, flight reservation and driving directions. If you go on Google, you would have seen driving instructions given. They are supposed to look at the shortest path. Now, the shortest path problem is first you have to have a directed weighted graph. So, it is a directed weighted graph. The path length we assume is the sum of the weights of the edges of the path. And the vertex at which the path begins is called the source, and the vertex at which the path ends is called the destination, and we will report the vertices in increasing order of the distance from the source. So, you start with the source, then the next one is reported first, then the next one. So, as increasing distance from the source, you will report the vertices. So, actually when you say shortest path, you are giving a list of vertices. So, construct the shortest path tree edge by edge. At each path step we are adding an edge corresponding to the construction of the shortest path to the current new vertex. So, from every node every vertex you start from the source, you go to the next vertex, from that vertex you take the shortest, from the next vertex you take the shortest and so on. Okay. Now, let us look at some notation that you use for shortest paths. First is for each vertex v, the small v is the vertex and capital V is the set of vertices. You have a delta s comma v, which is the shortest path weight. This is the actual shortest path weight between the source node and any other vertex v. Now, dv, which is the shortest path weight estimate. So, initially we assume that shortest path weight estimate, initially we assume that dv is equal to infinity, okay. And as the algorithm progresses, the dv, the infinity value or the cost value or the weight value will go towards delta SV, which is the actual shortest path weight. So, you are doing an estimate and starting with the worst case of infinity and trying to move towards the actual one. Then we have pi of v, which is a predecessor of v, that is a vertex v, on a shortest path from S. So, suppose you have S, A, B, C, then pi of v for S, for A is S, for B is A and so on. If there is no predecessor, for example source, the pi of that source will be equal to nil, and the pi induces a tree which is the shortest path tree. Now, that is the notation of shortest path. Now, let us look at the shortest path problem. So, the input obviously is a directed graph consisting of vertices and edges v and e, and you have a weight function that is associated with the edge e. So, the weight of a path is nothing but a list of vertices v 0, v 1 to v k, and the weight of the path is the I is equal to k v I minus 1 v I, that is the edge weight between v I minus 1 and v I in that particular path. So, the shortest path weight from u to v d u v will be the minimum weight if there exists a path from u to v, and will be infinity otherwise. So, if there is no minimum path, it will be infinity, and there can be multiple shortest path from u to v. It is not necessary it is a unique shortest path. You can have, depending upon the organization of the graph or the way the graph is organized, you can have multiple shortest paths, that is allowed. So, for any of the algorithms of shortest path, you have first an initialization. So, the initialization for the single source, I will come to that what is single source later, is the set V and S. So, for each V, that is each vertex belong to the set of vertices, we initialize d of v. Remember, this is the path estimate, d of v is equal to infinity, and we write the pi of v, remember this is the predecessor, is equal to nil, we assume. And then we initialize d of s, which source, s is the source node, ds of s, that is the that is equal to 0. This is the initialization. All the shortest path algorithm start with this initialize single source initialize this particular module. Now, now let us talk about what is the shortest path tree. For every node v belonging to the set V, pi of v is a predecessor of v in the shortest path from source to vertex, nil if such a predecessor does not exist. All algorithm will output a shortest path tree. The root is the source S of that particular tree, edges are pi of v v, pi of v is, remember, the predecessor of v, and the shortest path between S and v is the unique tree path from the root S to the vertex v. So, this is the shortest path tree. Now, let us take a small example. Consider the source node 1 and the destination node as 7. So, a direct path between nodes 1 and 7 will cost you 14. Okay. Now, you can have shortest path going from 1 to 3, 3 to 6 and 6 to 7. That will give you a path between 1 and 7 of cost 11. Now, you can also have 1, 3, 5, 10, I mean 5, 7, which will give you 15. So, it is higher. So, like this you can find there is only one, maybe more than one also, but here we have only one short up. We want to find the whatever exists, that particular shortest path. So, 1, 2, 1, 3, 6, 7 is the path. So, now if you look at this, the 3 there has predecessor 1, 6 has predecessor 3 and 7 has predecessor 1, that is the pi of 7 is 6, pi of 6 is 3, pi of 3 is 1, pi of 1 is nil. Okay. So, that is the terminology we use. Now, before we go further, let us look at the shortest path. There are many variants. The one simple algorithm is single source, single destination. It is called a 1:1. It is a 1:1. So, you have to find the shortest path from a given source to a given destination, given source S to a given destination vertex V. Then you have single source, all destination. It is a one to many type of algorithm, where you find the shortest path from the source node S to each and every vertex in the set V. Okay, small v. Then you have single destination to shortest path, that is many to one, where you find the shortest path to a given destination vertex T from each of the vertices, other vertices in the graph. Then you have all pair shortest paths problem, which is many to many, find the shortest path from u to v for every pair of vertices in the graph u and v. So, these are the 4 problems that you have with shortest path. So, single source, single destination problem and single source, single destination shortest path are sort of connected together, they are the opposite of each other. Now, if you take this particular shortest path variant, single source all destination, it has, and we assume we have a non-negative edge cost, we will come to this negative later. We need to solve or determine a shortest path from V to each of the remaining vertices of G of the graph. So, the single destination short, for example, here we have from single source V0, we want to find the path V0 V2, that is 10, V0 V2 V3 25, V0 V2 V3 V1 45, V0 V4 45. So, here you have from the single source V0, we have to find the shortest path to all the other vertices V2, V3, V1 and V4. So, that is the problem. Now, single destination shortest paths, find the shortest path to a given destination vertex T from every vertex. It is a reversing the direction of each edge to the single source and single destination problem. All pair shortest path, find the distance between every pair. This will have to call the other algorithm of single source, which we will discuss later. Now, before we go further, let us discuss some properties of shortest paths. So, first is the existence of the shortest path. Now, if some path from S to V contains a negative cost cycle, remember it is not only a negative cost edge, but a negative cost cycle. What is the meaning of that? That is again going round and round. There does not exist a shortest path. Otherwise, there exists a shortest SV, and that is simple. If negative cycle can produce arbitrary negative path by traversing the cycle enough times. So, negative weight edges may form negative weight cycles. Okay. If such cycles are reachable from the source, then the minimum cost between S and V is not properly defined, because you will be going round and round, you do not know when the path ends. Now, we go to a very important step associated with shortest path algorithm, that is the relaxation step. So, first we saw an initialization step. We initially assume that the estimate is infinity, and we also assume that the predecessor of every node is nil. Then we started the algorithm, and the source nodes the estimate is put, the actual distance is put as 0. Now, for each vertex V, we maintain an upper bound dV on the weight of the shortest path from S to V. So, what we do, for each vertex V, we maintain an upper bound of d of V on the weight of the shortest path from S to V. That means, initially remember it is infinity. Every time you do a shortest path, you just change it. If it is less than infinity, we put it. So, suppose dV is equal to 10 and you find another dV equal to 5, then you replace it. So, relaxing dV is initialized to infinity, as we have already discussed. Now, relaxing an edge uv is equal to testing whether we can improve the shortest path to V found so far by going through u. So, now assume that V has the the minimum weight as dV, and if you find that dV is greater than du plus the weight associated with uv, we can improve the shortest path, because now this du the going through u, okay, will give you a shorter path to V. So, dV becomes equal to du plus w, that is the weight of uv, and now remember the pi of V now becomes u, because u has been added. Now, if you look at this example that is given here, you have S u and then you have S v, and the distance between 5 and 9 is 2. Now, suppose you have u v w relax, what you will do is you will change that 9 there to 7. So, that means there is a node in between. But suppose you have u v 5 6 and you still the value does not change, then you do not change. We will understand this little more as we go along. So, after relaxation, dV will be lesser than or equal to du plus w u v, because you have you have put a new value for dV. So, relaxing an edge uv, that means actually when we talk about relaxation, we are considering relaxing an edge uv. So, you will relax an edge uv, testing whether we can improve the shortest path to V is found so far. So, associated with V, you will have a shortest path weight, and if you go through u, if it decreases, you update the dV and also the pi V. dV will be updated to du plus the weight of uv, and pi V will be u. A relaxation step may either decrease the value of the shortest path estimate dV and updates V's predecessor, or cause no change. That is, if dV is itself already lesser than this whatever you do, then du plus w, then there is no change. Okay. So, that is the relaxation. We will come into this later again relaxation we will discuss when we are talking about the respective algorithms. The next shortest path property is what is called the triangular inequality. So, if you have an edge uv and we have SV, SU plus W the weight between u and v, the weight of the shortest path from S to V is no greater than the weight of the shortest path from S to U and the weight of the edge from U to V. For all uv belonging to the edge set, we have delta SV is less than or equal to delta SU plus delta UV. So, this is what we say, this is the triangular property. If this will be true only if u is on the shortest path, we have the equality sign. Okay. Next is the optimal substructure property. It says that all paths of shortest paths are also shortest paths. For example, the shortest path problem has the following optimal substructure property. If node x lies in the shortest path from a source node u to a destination node v, then the shortest path from u to v is a combination of the shortest path from u to x and x to v. So, that is just it. Okay. Then we have the upper bound property. We always have that dV that we have estimated is greater than or equal to delta SV for all v, because the minimum weight is the minimum weight. All other estimates will be greater than this. The estimate never goes up. Relaxation can only lower the estimate, it can never increase the estimate. Okay. So, this is relax xv. So, initially you have S, V and when we did that S to V, you have changed the estimate to 2. We will come to this again in detail. Next, you have the convergence property. If you have S u v is the shortest path and if du is equal to delta of S u at any time prior to relaxing the edge S v, then dV is equal to delta S v at all times after relaxing u v also. So, this is called the convergence property, as you can see from the diagram. If dV is greater than delta S v, after relaxation dV will be du plus W u v. So, in this particular case dV will become 5 plus 2. Okay. Initially the V value was 8, now it dV value becomes, you can see that at the node V the value is 8, that is dV is 8. After adding u, you will get 5 plus 2 which is 7, otherwise the value remains unchanged because it must have been on the shortest path value already. So, because dV is greater than delta SV, okay, after relaxation. Now, the path relaxation property is the next property we will be talking about. So, P is equal to V0, V1, Vk, be the shortest path from S equal to V0 to Vk. If we relax in order V0, V1, V1, V2, Vk minus 1 Vk, even intermixed with other relaxation, we will get the d of Vk, that the last is equal to delta of the source to the last node. Okay. So, you can look here, the first node d of S is equal to 0, d of V1 is infinity, d of V2 is infinity, d of V3 is infinity and d of V4 is infinity. Now, first you start with S, because of that now d of V1 becomes 5, d of V2, okay, because d of V1 is equal to delta S of V1, then you have d of V2 is equal to delta S of V2 which is 7, 5 plus 2. Then delta V3 is 5 plus 2 plus 4 is 11 and 4 is 11 plus 3 14. So, you will see how we have relaxed in the order, we will have dVk is equal to delta of SVk. Okay. Now, shortest path predecessor subgraph property, once d of V is equal to delta SV for all V belonging to V, the predecessor subgraph is the shortest path 3 rooted at S. Predecessor graph will be G of pi is equal to V of pi, remember pi is the predecessor node. So, V of pi is equal to V belonging to that set of vertices and E of pi is the predecessor plus V, I mean the edge between the predecessor and V. If there is no path from S to V, then we always will have d of V is equal to the estimated and the minimum weight will both be infinity. So, what are some of the applications of this shortest path? Remember, when you say minimum path, it can be minimum total distance travel, it can be the total minimum cost of a minimum of the total cost of a sequence of activities or the total minimum of the total time of a sequence of activities. This can be used in many applications like network optimization, packet routing, image segmentation, computer assisted surgery, where you have minimum cost for the sequence of activities, computer games, DNA analysis, injection molding, scheduling problems, obviously production planning, reallocation of resources, approximation, and VLSI physical design. Lot of applications where the shortest path is very important. Now, let us now again talk about relaxation. All algorithms here will in this particular module will call initialize single source and then repeatedly relax edges. Relaxation is the only means by which shortest path estimates and predecessors can change. Remember, the estimates started with infinity, it can change, and the predecessors will also change. Now, the algorithm, there are different algorithms which can be used to find the shortest path. The algorithms differ in how many times they relax each edge and the order in which they relax the edge. So, Bellman-Ford relaxes each edge many times, while Dijkstra's and the algorithm for direct acyclic wraps relax each edge exactly once. So, there are basically two algorithms. Dijkstra's algorithm. In Dijkstra's algorithm, negative weights are not allowed. In Bellman-Ford algorithm, negative weights are allowed, but negative cycles reachable from the source are not allowed. That is the only condition. Operations that are common to both the algorithms, which we have already discussed, is the initialization and the relaxation. Now, let us look at the Dijkstra's algorithm. The distance of a vertex V from a vertex S is the length of the shortest path between S and V. We have already seen that. Dijkstra's computes the distances of all the vertices from a given start vertex X. The assumptions are the graph is connected, the edges are undirected, and the edge weights are non-negative. So, grow a cloud of vertices beginning with S and eventually covering all vertices. We store with each vertex a label dV, that is, remember the estimate, represent the distance of V from S in the subgraph consisting of the cloud and its adjacent vertices. At each step, we add to the cloud the vertex U outside the cloud with the smallest distance label. We update the labels of the vertices adjacent to that U that you have now added to the cloud. So, this is edge relaxation. Now, consider an edge E which is UZ, okay, an edge connecting U and Z. Use the vertex most recently added to the cloud. Now, Z is not in the cloud. Now, the relaxation of edge E updates the distance of dZ as follows. dZ is the minimum of dZ and du plus E. So, du plus E is 60 and dZ originally for some reason it has been calculated, I mean it has not for some reason, in some step it has been calculated as 75. Now, because of the edge from the the lower edge, now it has become dz equal to 60. So, that is the edge we have to consider and the other edge is removed. So, this is the edge relaxation. This example has been adopted from this and you will see here we start with A, it has a value associated with it as 0, then you come to C, the cloud grows and you have C is associated with remember d of A is 0 and d of C is initially infinity. Now, it has been updated to 2 because 2 is less than why 2 because it is 0 plus 2. Okay. Next you go to the next node which is 3. Now, 3 has 3 could have been reached from A or it could have been reached from C. Now, if you take it from C, you have the value as 3. Okay. The next node that you can add is E. When you add E, the value becomes 2 plus 3 5 and then you can add some of the edges are removed as you can see. Next you have added B. B gets 3 plus 2 5 plus 2 7 and then finally you add 9 which where you have to add 9 from 3 plus 5 8. So, some of the edges which come to 8. Now, let us see what are the edges that are removed. D comes from A and C, but if you come from C it is 2 plus 1 3, if you come from A it is 0 plus 4 4. So, you do not consider that edge. Now, let us look at B. B has edges coming from so A, C and E. Now, A has 0, 0 plus 8. So, you have B, D of B as 8, 2 plus 7 9 and then you have 3 plus I am sorry 5 plus 2 7. So, 7 is the lowest. So, that is the edge you will consider and the other 2 edges are removed and so on. Now, how is the Dijkstra's algorithm implemented? A priority queue stores the vertices that are outside the cloud. The key will be the distance and the element will be the vertex and you have locator based methods. Insert k comma e returns a locator, replace key changes the key of an item. we store 2 labels with each vertex, the distance and the location in the priority queue. Now, Dijkstra's algorithm assumes that the weight of the edge is greater than or equal to 0 for each edge in the graph, okay. That is, there is no negative. Maintain a set S of vertices such that every vertex V belonging to the set has dV is equal to delta of S comma V, that is, the shortest path from S to V has been found. Initial values, of course, the set is empty, D of source is equal to 0 and D of V is equal to infinity. Now, you select a vertex U that is from V, that is not in S, such that the D of U is equal to the minimum of D of X, where X belongs to V minus S, and then the new set becomes S union with this set. For each node V adjacent to U, you have to do a relaxation of, for each node V that is adjacent to the U you have included, you have to do relax U V W, where W is the weight, and then you repeat the steps until the set originally starting with an empty set becomes contains all the vertices. So, the analysis of this is the graph operations method. Method incident edges is called once for each edge, and the label operations we get the distance and locator labels of vertex set, and setting and getting the label takes of the order of 1. The priority queue operations, each vertex is inserted once into and removed once from the priority queue, where each insertion or removal takes of the order of log n. The key of a vertex in the priority queue is modified at most degree W times. Remember, degree W is the number of times that particular node is associated with a weight, where each k changes, each key change, that is, if it is takes 0 to the log n time. So, Dijkstra's algorithm runs in of order of n plus m log n time, provided the graph is represented by the adjacency list structure, where we recall that the degree of V, the summation of the degree of V is 2m. The running time can also be expressed as m log m, since the graph is connected. Now, what are the features of the Dijkstra's algorithm? First of all, it is a greedy algorithm, because it selects the one that gives you the minimum, visits every vertex only once when it becomes the vertex with minimal distance among those still in the priority queue. Distances may be revised multiple times. Current values represent the best case based on our observations so far. As you make observation, this may change. Once a vertex is visited, we are guaranteed to have found the shortest path. So, this is an example again taken from this particular thing. So, we let us look at this. So, you start with C, and now C has 0. Now, there are two updates that come. So, C can be connected to A, and there it is 9 the D value, and C can be connected to E with 8 value. Now, so this is the next that will be selected with the one with the minimum. So, you select that. Now, from E you could have made you could have gone to D, which will give you a value of 8 plus 7 15, or you could have gone to G 8 plus 1 9. So, you will select 9 as the next one in the cloud, I am sorry, and you have a 9 there also. So, you can select that. So, that is selected. You could have selected this G or A. So, we select that. So, that 9 is collected. Now, 9 is connected to D by 4. So, 13, and A is connected to D by 14, 9 plus 4 13, and A is connected to B by 9 plus 2 11. Now, you have 3 13 11 and 0. So, and a 9 there for the G. So, that is connected, we took that G first. So, now connecting G you have only a 4, 2, you do not connect the 4 because that already you have considered E. So, you have a 2 connecting there, that becomes 11 again. So, the next one is you could have selected B or F, we select B. So, that comes into the node, and the next is the 11 one, because 11 plus 2 is 13. So, that you should not consider. So, you connect that, and then you have an H going there as 14 and 13 here. So, D is connected next. So, that is connected, and finally, F is connected. So, after you have done this, you can see the path that is followed: C to E to G to F to H, and C to A to D, and C to A to B. So, that is a, so from C if you want to go to H, the path is C E G H, and if you look at this, G has predecessor E and so on. and if you want to go to F, the path is CEGF. If you want to go to B, the path is CAB, and if you want to go to D, the path is CAD. So, that is the path you have, the path is given. So, that is it once you have covered. So, in this particular module, we discuss the Dijkstra's algorithm and explain the shortest path. Before we explain the Dijkstra's algorithm, we discuss the shortest path and problem, the basic problem and all its variants. Then we discuss some properties associated with the shortest path, and then we outline the Dijkstra's algorithm, and then we illustrated the Dijkstra's algorithm with an example. So, in the next module, we will be talking about another shortest path algorithm, famous maybe two shortest path algorithm, the Bellman-Ford algorithm and another algorithm for all paths algorithm. So, this is what we will be talking about in the next module, and that will complete the graph algorithms that we have been discussing thus far. Thank you.